As Juliet said, we're really excited to welcome Dr. Kelin Wang to his talk today on Megathrust strength and stress with implications to earthquake processes. And he joins us from the Geological Survey of Canada. Great, and I just wanted to do a quick introduction for what SCNet is and why we're kind of holding this workshop this week. So SCNet is the international component of SZ4D, and it's a coordinated network of working towards building an international community, studying subduction zone geohazards, specifically defining the limits and possibilities for predicting geohazards. And we've got three kind of key goals here that we want to outline as part of our mission. And so our goals are to compare the observations of subduction zones around the globe with a common data set and understanding, to cooperate, to consistently instrument critical subduction zones that can provide key and transferable insights, and to develop and nurture an international and diverse cadre of early career scientists that is equipped to make the necessary breakthroughs. And we would love your feedback. So if you are willing to use your phone to take a QR code, or to kind of take a photo of it, to use the QR code scanner. The one on the left is kind of for suggesting topics or speakers, and the one on the right is going to be a demographic survey for attending this event. And we'd appreciate any of your input. And with that, we're excited to welcome Dr. Kelin Wang. He will be speaking to us about subduction zone strength and stress with implications for earthquake processes. He is joining us from the university, or the Canadian Geological Survey. He got his BS from Peking University in China and his PhD at the University of Western Ontario. And we're really excited to have him speak today. So with that, Dr. Wang, the floor is yours.
I believe you're muted.
Okay. Oops. Okay, now it's working. Is it working now?
It's working. We can hear you.
Oh, okay, thank you. Yeah, thank you very much for giving me this opportunity to share some of the research ideas and results with the audience. Yeah, I quite enjoyed the talks for the past 2 days. I missed the first day because I was traveling, but I learned a lot from the other talks yesterday and this morning. Yeah, it's a pleasure to share some of my knowledge on this subject. So I will talk about the megathrust strength and stress, and with implications to earthquake processes. And I will discuss 3 issues. And one is the how do we define the megathrust strength, and with ideal and real thoughts. And the second is how we constrain the strength at a regional scale using 2 different methods, and also the importance of knowing the absolute strength of the fault in understanding the physical importance implications of stress drop in earthquakes. And the third is I'll talk about some of the implications on earthquake processes from 2 perspectives, rheology and petrology. Okay, let's start with the first one. How do we define?
Dr. Wang, you haven't shared your screen yet with your
No?
slides. Not yet.
That's interesting. Let me just check. Okay. Yeah, can you see my slides? Okay, thank you.
We can see them now. Thank you.
Okay. So anyway, I will talk about 3 things as you see on the screen now. And first is define the strength. What is strength? And for ideal and real faults. And the second is how do we estimate the strength, constraining it at a regional scale. The third is implications and to earthquake processes from two different perspectives, rheology and petrology. Let's start with the first one. We start with ideal faults. For ideal, a creeping fault, and it's very simple because if it's always at failure, and so there's just one strength, it doesn't change for in ideal situation. So that's our strength. It's very simple. But different faults may have different strengths. Some faults can creep against low resistance. Some can creep against much higher resistance, such as those very rough faults. And we call that kind of creep strong creep. For ideal stick slip faults, and it's a bit more complicated. And when the fault is locked and it doesn't do anything, but when it slips in an earthquake, the stress and strength changes because earthquake slip involves weakening. At the time of the earthquake, the fault, as you can see from here, the fault is below failure, except at the point of initiation. And so this is the strength, we call it apparent strength. And this is strength we can basically observe and estimate. And when the rupture front comes to this point, it'll raise the stress to its failure threshold. And we call this the true strength. And true strength is something and we really cannot observe directly. And normally we're not too interested about it anyways. And as the fault slips and it weakens, and as it weakens, we have this dynamic strength. And this is the stress that produces frictional heating. Here, for simplicity, we assume that the dynamic strength is the same as the final stress, but it's really probably not the case, but for simplicity, and this is the assumption we usually take. And the difference between the apparent strength, that's the stress before earthquake, and the dynamic strength, that's stress after earthquake, is a static stress drop. So for ideal faults, and we have for ideal creeping faults, we have just a simple one strength, and for ideal stick slip faults, we have three different strengths. And the real faults are complicated. And as you can see from here, this picture, and also from the nice talks given by Whitney Baer and Anna Onken over the past 2 days. And the real faults are very complicated, and it consists of many different materials and small slip zones, shear zones inside. And however, we need to parameterize it for our scientific research. So different ways of parameterizing a real system with fewer parameters. And the simplest one is that the largest regional scale, and we just simply consider a simple situation like this. And the shallow part, it will be the frictional regime or the brittle regime, and deeper part, when the temperature is higher, we had viscous creep. That's two different regimes with the transition in between. And the main characteristic of the frictional regime is it's a pressure sensitive, regardless of its whether it's a single plane or a zone, and its strength, integrated strength over the zone, is pressure sensitive, and it's normally it's parameterized using the friction law like this, with a single friction coefficient, mu prime, effective friction coefficient. And so the shear stress is proportional to normal stress. And the friction coefficient here, mu prime, includes two things. One is the intrinsic friction coefficient here, and the other is porphyry pressure. If we prefer to use the true friction coefficient, then we can define effective stress this way: the real stress minus porphyry pressure. Or alternatively, or equivalently, if we prefer to use a real normal stress, we can define a effective friction of coefficient friction. That's here, mu prime here. And assuming that a porphyry pressure ratio can be defined as shown here. And here the normal stress for a weak fault, for a fault like this, is approximately the lithostatic pressure. Okay, so that's the frictional regime. And for the deeper part, the viscous regime and the deformation is sensitive to temperature instead of pressure. And here we have a few more parameters, and depending on what material is involved, it could be either parallel creep or some other more complicated creep, such as low temperature plasticity flow loss. And so for a stick slip fault, what kind of brittle strength or the frictional strength are we talking about, right? We're talking about three of them, right? And basically, and the relation between three is something like this. But in the normal case, in normal situations, we don't really consider the difference between them, and for most purposes. But for specific purposes, such as if we talk about stress drop, we'll have to discuss the difference between the apparent strength and dynamic strength. Okay, then we come to our second subject, that is how we constrain the fault strength at a regional scale. At a regional scale, there are only two ways to constrain the fault strength. One is force balance, the other is frictional heating. Force balance. If you consider the fork, and the stress in the fork is really controlled by two competing factors. One is the megathrust here. The megathrust here causes compression. And the other is gravity. In the presence of margin topography, because we have this slope, and gravity causes extensional stress. The actual stress observed in the fork is the result of the competition between these two. If the horizontal stress, if the megathrust is weak, and the horizontal stress is smaller than the vertical stress, and we have this situation. Otherwise, if the fault is stronger and the horizontal stress is larger than the vertical stress, because the vertical stress is basically just the weight of the rock column above, and we know its value. And because we know the value of the vertical stress, by comparing the two stress components, we can infer the absolute value of the stress on the megathrust. So that's the idea. And to make the long story short, it turned out that the stress in the fork here is pretty neutral. That means the horizontal stress and vertical stress for most subduction zones are pretty similar. There's not a big difference. And consequently, and the stress, and we can determine the stress from this kind of neutral state, almost neutral state, by calculating the force balance. And this is the result derived by Diofolder et al. Recently. As you can see, And in terms of the effective friction coefficient, mu prime, and the strength of the fault is of the megathrust in all these places is pretty low. And these are small numbers. I'll come back to explain why these are very low numbers. And one important case is the Japan trench here. And because of this earthquake caused a devastating tsunami, as we all remember. And this is the slip distribution here as the average of 42 published slip models for this earthquake. And from this model slip distribution, we can calculate the stress induced in the shallow crust of the upper plate, as shown by these arrows here. And this stress causes a reversal of the state of stress in the forearc. Before the earthquake, and the forearc is mostly in compression. But after the earthquake, because of the tension, the tensile stress induced by the earthquake, and the forearc turns into a mostly extensional. So this normal faulting earthquakes became more dominant. So this stress reversal and this stress change is really caused by the stress drop of the earthquake. And this stress drop is derived from the slip distribution I just showed in the previous slide. So if you look at the a two-dimensional view along a central corridor, and the stress drop along the megathrust is something like this. It's on average, it's just a few megapascals. And a few megapascal stress drop is enough to cause this stress reversal. That means the state of stress in the upper plate must be fairly close to neutral. We can use this stress drop and to construct a two-dimensional model to see how this reversal happens. And this is the stress state in the model before the earthquake. And this state of stress is obtained using a friction coefficient as small as this, similar to what Diefalder was using. So that's the stress along the megathrust. This is the stress in the upper plate here. And at the time of the earthquake, because of this stress drop, and we have an incremental stress change as shown here, this stress drop causes this stress change here. And the stress before the earthquake plus the stress change lead to the stress after the earthquake. And this dashed line is the stress along the megathrust after the earthquake, and simply the stress before the earthquake minus the stress drop. And this is the stress after the earthquake. So as you can see, much of the forearc here is now in tension, in extensional state. If the friction coefficient is larger or if the fault is stronger, we would not have extension after the earthquake. But if the fault is much weaker than this, we would not have compression before the earthquake. And the stress reversal before and after this earthquake really provided pretty strong constraints on the strength of the megathrust here. The next method of constraining the strength at a regional scale is using frictional heating. And the thermal structure of subduction zones can be fairly, well, I will say this, the thermal modeling of subduction zones is pretty mature by using the kinematic parameters, plate age, and the geometrical information. We can predict the thermal state. And if we have good heat flow observations, we can also constrain the frictional heat, the amount of frictional heat on the megathrust. And heat flow is difficult to obtain, but in a few places we do have adequate heat flow data to constrain frictional heating. And heat flow is measured usually using heat flow probe like this. And I was involved in some of the measurements. That's me putting a tag here. But there are also other methods such as using gas hydrate, BSR, and other things. And from heat flow data and thermal modeling, and we can determine the apparent coefficient of friction here. And the important message from this compilation results is that most of the megathrusts, especially those that produce large earthquakes, are very weak. And therefore, no locked megathrust is really strongly coupled. They're all very weak. They're all weakly coupled. And the other important thing that I would not really discuss in this talk is the strength variation as a result of the roughness of the fault. And towards this end, the fault is very rough and it's really mostly creeping. That's the strong creep I mentioned earlier. And toward this end, the fault is much smoother and they produce large earthquakes. But at the same time, they are much weaker here. Okay, so I've explained how we constrain faults at the strength at a regional scale. And now let's have some discussion about the strength. The first question is with these two methods, what strength have we determined? And for stick slip faults, we talked about three different strengths, right? And for stick slip faults, highly seismogenic faults, what we determined with the force balance method is pretty close to the apparent strength. And with the frictional heating method, what we determined is really the dynamic strength because heat is produced only when the fault moves, as shown here. And when I say it's close to this, because when we determine fault strength from 4-arc stress, and in most cases, the fault is locked, it's not at this failure strength here, this apparent strength here, maybe lower than this apparent strength. And so there's a range, and we don't know where we are in this range. And frictional heating, certainly that's simple. It's just the stress during slip. And the difference is not very large, but I will talk about the difference just immediately. And the next question is, how weak is this number or that number? These are the numbers you've seen on the screen earlier. And I said they represent a very weak fault, weak megathrust. And the comparison, the reference for the strength or weakness is really the Byerlee's law. With Byerlee's law, with a friction coefficient of about this value, about 0.7, and if you assume hydrostatic profile pressure, which is about 0.4, and the effective friction of coefficient is about 0.4 here. And that's what we mean by a strong fault. Therefore, a value as small as 0.03 or 0.13, these are much weaker than our reference strength. That's why we say megathrusts are weak faults. Then the next question is why they are weak. And they are weak, first, is because the actual intrinsic friction, mu, is much lower than that of Byerlee's law. And that's been concluded by many other studies. I would not explain the detail, but the fault gouge is usually is much weaker than the when you put two hard rock surfaces together, and that's what the Byerly's law was based on. And also the pore-through pressure ratio. The pore-through pressure is certainly much higher than hydrostatic, and that's for sure. Exactly how high, we don't really know. And so the combination of these two factors makes the fault very weak. In addition, rupture dynamics also plays a role, especially if your strength is determined from frictional heating. And because that's really the lowest strength of the three options, and so that also plays a minor role, but it's not that important for megathrust. So next question about regional strength is stress drop. And it's important to ask how large is the stress drop as compared to the absolute strength of the fault. Now we can do a back of envelope estimate. With this friction coefficient here, suppose we are at 20 kilometers depth. And because the normal stress is basically just the weight of the rock column above it for a weak, horizontal weak fault here. And using reasonable density estimate assumptions such as about 3, and at this depth, the shear stress is really 20 megapascals here. And the stress drop in megathrust earthquakes is a few megapascals, as compiled by many authors, such as Ye et al. And for global megathrust earthquakes. If you assume the stress drop is 4 and the absolute strength is 20, we're talking about 20%, 25% stress drop here. Therefore, stress drop is a significant fraction of the absolute strength. And this conclusion has tremendous scientific and practical importance. The first scientific importance is it clarifies two misconceptions. First is the stress drop in earthquakes is tiny as compared to the absolute strength, such as 1%. This would be the view held in the 1980s or earlier. And certainly this is not the case. And the other misconception is the stress drop can be complete. And it's, this notion became somewhat popular after the Tohoku-Oki earthquake because of large slip. But as we can see, the absolute complete stress drop is also not possible. It may be possible locally in a small area of the fault, especially at a shallow depth, but certainly not possible at a regional scale. The other important scientific importance is because the stress drop is a significant fraction of the absolute strength, and the stress drop in an earthquake cycle, and after an earthquake, and to rebuild stress to the next earthquake, it takes time. Therefore, the concepts of characteristic earthquakes and recurrence intervals are valid. They do have a physical basis. And the third importance is the energy partitioning. Earthquakes consume energy mostly via thermal dissipation. And now we're back to our ideal stick slip faults and creep faults here. Now the time goes up, and when we have an earthquake here and here, that's the during slip here, and the energy partitioning is shown here. Because of the stress drop is only about 20%, and from here before earthquake to here, and most of the dynamic strength is here. Most of the energy is consumed by frictional heating here. So this is the dark part here, the largest part of the energy consumed by an earthquake. In comparison, the energy radiated by using a seismic wave is a smaller component, and even smaller is the fracture energy there. In comparison, the weak creep may or may not dissipate more energy than a slipstream fault here. This weak creep. However, if we have a strong creep here, but those are very rough faults, the energy dissipation can be a lot larger and heat flow can be much higher there. Okay, now I've explained how we constrain regional fault strength and implications to stress drop. Now we can go ahead to talk about earthquakes. So I will talk about two things, right? The first thing is pretty obvious, just a reiteration of the notion of the rheological control, friction to viscous transition. And the other, the petrological control, involves a new hypothesis. Rheology. And rheology is controlled by temperature, right? And if you have a old and cold subducting plate, such as in Northeast Japan, and you end up with a very cold megathrust. As a result, the frictional to viscous transition is much deeper. And earthquakes occur only in the frictional domain. And when it's viscous, really, it may be that rupture may dynamically extend into the semi-frictional area, but wouldn't go very far. So basically, the frictional regime constraint determines the seismogenic limit of the megathrust. And if the subduction zone is much warmer, such as Cascadia, and the frictional regime ends at a much shallower depth, so a megathrust earthquake can only extend to a fairly shallow depth. So that's basically just the rheological control. But if the fault is, if the subducting plate is old, but the fault is strong, and you can still make the megathrust warmer, in this case, the frictional to viscous transition can still be shallow, but this is pretty rare or probably absent in this situation for large earthquakes. So that's about rheology. However, the rheology only determines the maximum extent of rupture, the possible potential seismogenic zone. And what actually happens is determined by other things, right? And first is, of course, geometry. If the megathrust is very rough, you really cannot have a very large earthquake. If you assume it's smooth enough to hold a big rupture, and then whether a rupture can occur, it is determined by how the friction coefficient changes with slip or slip rate, not by its absolute value. It's the complexity in the change of friction that gives rise to soft barriers to a seismic slip. So I will focus on the soft barrier here. That is the mantle wedge corner here. That involves a new hypothesis. As we all know, the subducting plate dehydrate to provide water and to hydrate the mantle wedge. The mantle wedge spandinized to create serpentine and other minerals. And as we go from the mantle wedge corner to greater depth along the megathrust, we first the serpentine minerals is first the low temperature type lizardite or chrysotils, mostly lizardite. At greater depths, it becomes mostly antigarite. And the transition from lizardite to antigarite is, there are different models, but there's certain uncertainties. And as shown by the difference between these two models on the screen, the second model involves two reactions as shown here. Regardless of the complications, and it's important to recognize that the lizardite to antigarite transition takes place in a temperature range about 300 to 400 degrees. And we assume that the serpentinite from the base of the mantle wedge is entrained into the megathrust to affect its frictional behavior. But how this the serpentinite affect the frictional behavior depends on the frictional behavior of the two different serpentine polymorphs. Okay, and based on numerous laboratory experiments, lizardite or chrysotile and exhibit velocity strengthening under all lab conditions. So they tend to impede seismic rupture. And at high slip rate, they can exhibit some mild dynamic weakening. So they may allow rupture propagation, not always stop the seismic slip. So that's lizardite. Antigarite is different. Laboratory experiments show that under certain conditions, especially when the temperature is higher, they can be seismogenic. At low rate, can be velocity weakening, so it can initiate rupture. At high rate, and many experiments show that dynamic weakening happens quite commonly, and so the strength drops very sharply as slip begins. That's the aerodynamic weakening. That will facilitate rupture propagation. Therefore, we know that lizardite or lizardite antigarite tends to impede seismic rupture, but cannot always stop it. But antigarite can facilitate seismic rupture. Therefore, we have this hypothesis that the lizardite-rich antigarite at the mantle wedge corner here, from both subduction zones, forms a soft barrier to seismic slip. And the deeper antigarite patches may hold small earthquakes, and dense collection of these patches may host large earthquakes. And until a larger depth and viscous creep prevails. Okay, now we can test this hypothesis by looking at the Chile margin. Along Chile margin, there are many large earthquakes that occurred recently and recorded in modern networks. The slip distribution for these events is pretty well determined. And the mantle wedge corner, this green line, is also fairly well constrained. I will not explain details for this, but what we focus on is the comparison between the slip and the mantle wedge corner. As you can see from this rough schematic illustration, the mantle wedge corner does play a role here as a soft barrier here. Let's look at the northernmost events first. There were two earthquakes in this year, and one of them is an aftershock, and this distribution is shown here by one group. And the aftershocks undoubtedly shows a bimodal slip distribution. And 6 different groups, they determine the slip distribution. They all show the bimodal distribution, as shown here. The main shock is a bit more complicated. Some groups found bimodal slip, but some others do not. Therefore, the bimodal distribution is for sure happened for the aftershock and possibly for the main shock. And it appears that the rupture started the up dip of the mantle wedge corner and propagated up dip and down dip and through the barrier and triggered a deeper slip here. Now we can construct a thermal model, and I will not explain the details of the modeling method and here, but I'll just show the results here. And here I show two sets of temperatures. One is the purple lines is the situation without antigarite. And the black ones is the situation with antigarite. And this the temperature along the megathrust, the plate interface. This is the stress distribution, shear stress distribution along interface. Here you can see the brittle ductile frictional viscous transition here. And shown here is the situation assuming there's no antigarite. So the fault zone is quartz ridge here. And in this case, the seismogenic zone extends to this depth, to the semi-frictional regime, and the observed, the rupture depth is much deeper than that. And if you introduce antigarite, the antigarite patches that I explained earlier here, and the rupture can go much deeper in the model. It's more consistent with the observed rupture distribution. More importantly, if you look at the mantle wedge corner here, you can see, and it is lizardite rich, and it becomes antigarite rich at greater depth. Therefore, the model also predicts a lizardite-rich soft barrier consistent with this bimodal rupture distribution here. We can change parameters and friction coefficient and flow law parameters. The details will change, but the big picture stays the same. We can look at the other earthquakes. And for this event, for this event, the slip is confined to be down dip of the mantle wedge corner. The rupture started at large depth, propagated down dip, and never made it through the barrier. For this event and the Illapel event, and the rupture, the slip, managed to get through the barrier, but only in the central portion. And for the two sides, it still had difficulty going through the barrier. For these two events, the slip, these are larger events, the slip got across the barrier here. For this one, the epicenter is shown to be down dip of the mantle wedge corner, but there are uncertainties in both the epicenter location, especially in the mantle wedge corner location. So I think it's very likely the rupture actually started above the mantle wedge corner here, like for this event here. Another piece of evidence to support the presence of the soft barrier. Oh, okay. Yeah, before that, I only show the thermal model results for these other events together with the quickie event there. For all these events, if you look at the stress distribution along the interface, the seismogenic zone extends to a fairly large depth, over 50 kilometers, and consistent with the observed slip distribution. And for all these areas, there is the lizardite-rich soft barrier is present, and that explains all the three types of three modes of slip observed along this margin. The bimodal slip, a slip confined to be down dip of the mantle wedge corner, and the slip mostly above the mantle wedge corner, but extended down dip of the corner here. Another piece of evidence for the presence of the soft barrier is aftershock distribution. And for these two earthquakes, the aftershock distribution here. These are the events on the interface, and this gap here in the middle here, certainly that's consistent with the lizardite-rich soft barrier, and the deeper cluster of aftershocks is consistent with the antiquarite-rich patches here. Now the next question is what happens to the south? And the very southern portion of the margin, including the rupture area of the 1960, the southern half of the 1960 big earthquake, and this small earthquake in 2016 that did not rupture through the mantle wedge corner. And because the high temperature in this area and the mantle wedge corner and the serpentine mineral is mostly antiquarite already, so there's not a lizardite-rich soft barrier for this area. Then the question is why these little earthquakes still stopped by the mantle wedge corner. Now we look at some other even warmer subduction zones. These subduction zones produce the ETS or ETS-like phenomena at the mantle wedge corner here. And as explained in this earlier work, that the ETS occurs here, and because of the petrological processes of the mantle wedge corner, because of this the formation of the large amount of dehydration of the warm slab at shallow depths, providing a lot of liquid for the mantle wedge corner to cause serpentine or antiquarite saturation here, and to cause other petrological processes. In the end, it provides a permeability seal to allow very high porphyry pressure to be developed. And this high porphyry pressure is the geological condition for the ETS behavior here. And the other important condition for ETS to occur is that the megathrust rupture has to be confined to a depth shallower than the mantle wedge corner. If it's deeper than the mantle wedge corner, ETS does not occur. So these are two conditions: high porphyry pressure, and the seismogenic zone is shallower than the mantle wedge corner. And both conditions are met at very warm subduction zones, as these ones. Back to Chile. And this area is not as warm as Nankai and Cascadia. Here I show the Nankai and Cascadia temperature and stress along the megathrust here. And the mantle wedge corner is also deeper in those places. And this is the weird high porphyry pressure area. And that's our ETS zone for Cascadia and Nankai. And for southern Chile, as shown from here, the seismogenic zone can go a lot deeper. Therefore, we do not have the ETS. However, because it's also warm slab subduction, and we expect a lot of fluid, dehydration of the slab takes place at fairly shallow depth. Therefore, we still may have a zone of high porphyry pressure at the corner. Therefore, even though the ETS does not occur because of the seismogenic zone extends to greater depths, because of the presence of the high porphyry pressure, it is possible that the high porphyry pressure serves as a very gentle barrier to a seismic slip. There's a laboratory evidence that the high porphyry pressure tends to stabilize fault slip. They make the fault weaker, but as they slip, there tends to be more velocity strengthening, less velocity weakening. So it is possible that this very gentle barrier may stop small rupture like the 26 event here, but cannot stop the large rupture like the 1960 earthquake there. So in summary, the petrological control is, I focus on the soft barrier at the mantle wedge corner because of presence of a lizardite-rich serpentinite in the fault zone. At a deeper part of the fault is an antigrade-rich serpentinite can facilitate rupture. And I also mentioned that for very warm subduction zones, and the behavior is different. Here we have ETS. We have a high pressure antigrade-rich ETS zone. And one thing I did not cover is a similar situation at the very shallow end of the megathrust. Here we also have a soft barrier as concluded by many other studies, and we have a lot of clay minerals there, may tend to impede seismic slip, but cannot always stop the slip. Therefore, I've so far covered all the three points I want to discuss. I've defined the megathrust strengths for ideal and real faults, and in a parameterized way. And also, I've also explained how we constrain regional scale megathrust strength using force balance calculation and frictional heating estimates, and its implication to a stress drop. And I've also explained discussed the strength and seismogenesis from the perspective of rheological control and the perspective of hydrological control. Thank you very much.
Thank you. I want to open the floor now to questions. Feel free to ask questions via the Q&A feature or through the chat.
Oops. So either I explained the whole thing very clearly, or didn't explain it at all.
Maybe it's, yeah. I'm going to give people a couple minutes just in case they're still thinking. And I'll take a second to just invite everyone again to the breakout sessions that are tomorrow. We have a breakout session focused on rheology, one on stress and one on timescales. And the full schedule is on our website, and they will all be using the same Zoom link, which everyone should have access to. If you registered, it should have been sent to you in an email, and I will also put it in the chat. Oh, we have a question. Fantastic, from Zhengji Li. Fantastic talk, Kelin. The day before yesterday, Dr. Jim Morey concluded that the dynamic friction coefficient is about 0.1 compared to the static friction coefficient, which is about 0.6 in Firely's law. Considering this difference, would it be easier for us to explain the data better?
Sorry, I missed the Jim Morey's talk because I was flying. I was flying back from Europe. Yeah, I understand the result is from mostly from the drilling of the shallow part of the fault, right? And so there's some extrapolation to do, right, to determine the strength of the friction coefficient for the deeper fault. Assuming this the extrapolation is valid, and then we have the question of real friction coefficient, the like 0.6 from Byerly's law. That's the intrinsic friction coefficient from Byerly's law, and versus the effective friction coefficient that includes the role of fluid. Yeah, and so I'm not sure the comparison is made. The latter is I think the comparison with the effective friction coefficient is probably more straightforward, and in that case, it will not be 0.6, right? It'll be much smaller. I'm not sure if I addressed the question.
I'll please feel free to put in the chat if you have any other thoughts. But we have another question from Kelin Wang. Thank you for the great talk, Kelin. Is lizardite and inigorite observed in exhumed subduction zones at this PT conditions, maybe a paleosubduction zone with a similar PT path?
The problem is when geologists study cementinite, it's not always from the mantle wedge, right? And sometimes they find the analogs. It could be due to a different geological past, but it's considered to be very similar to mantle wedge, and so determine the various things. Yes, they are indeed observed. If you remember the two models for lizardite to antigerite transition, right? The first one, the gray band, is based on theoretical thermodynamic calculation by Evans. And the other one, involving two reactions, that's actually determined by measuring samples collected from the field, from alpine cementinites in Europe. So yes, they are indeed observed and actually determined the transition, the PT condition from real samples.
Thank you. We have one more question from Shuama. Nice talk, Kelin. In Hasegawa's revised aftershock locations, normal earthquakes seem only located near the plate interface or the free surface. Not many normal aftershocks were in the wedge. Does this imply the stress state in the wedge may be different from your calculation?
I understand there are some uncertainties in terms of the earthquake location and stress. If you look at the paper I quoted, 2019, Wang et al. JGR paper, and there are two groups that located these earthquakes, and the other one also from Tohoku University, and it's can't remember the first author's name. It's a lot more comprehensive because they use a different method to using waveform similarity. They managed to locate a lot more earthquakes, and yeah, they concluded indeed a lot of the normal faulting earthquakes are indeed in the upper plate. So I understand there are some uncertainties, but I think the consensus still is that yes, the stress is reversed by that earthquake.
Great. The questions are pouring in. We have another one from an anonymous attendee. In the first half of the talk, you suggested that megathrust earthquakes occur when the regional scale friction is very low, potentially due to high pore pressures. In subduction zones where there is not a high pore pressure to facilitate ETS, not very warm subduction zones, are pore pressures low enough to impact slip in the antigerite-rich zone?
Yeah, I'm not sure if the question is framed as intended, but I didn't mean the high pore fluid pressure causing a weak fault leads to earthquakes. And I really didn't examine that relation. I don't really think there is such relation. To me, it's the earthquake rupture. Firstly, is harbored by a fairly smooth fault. You need the geometrical and structural condition to host a large enough rupture. And second is by the frictional behavior of the material in the fault zone, whether it's a velocity strengthening, velocity weakening, or dynamic weakening. So these are the key factors. And porphyry pressure does play a role. And as we all know, if the porphyry pressure is high enough, it tends to bring a locked fault closer to failure. So failure is easier. But a lot of the recent studies, especially laboratory studies, indicate, even though it makes the fault weaker, but it tends to make the fault less seismogenic. So as it slips, it tends to be less velocity weakening. So these are the complications. I think these things are still evolving. We'll see how it develops. The community is trying hard to work on different samples in the lab to determine the behavior.
Great, thank you, Kelin. That's all of the questions we have. And since we've reached the top of the hour, I want to thank you for this fantastic talk. I want to thank you for taking the time, and I want to thank everyone who attended for coming and listening and being a part of this workshop. We will have this talk up on YouTube in a couple hours, and we'll send a reminder about all of the discussion sections happening tomorrow and Friday. We hope to see you all there, and thank you again.
Thank you. Bye.
Bye.